Welcome back. Today we're going to learn about alkynes and how to synthesize them and what type of reactions we can do to make a specific kind of products. All right. Now you're all familiar with alkynes from when we learned nomenclature. Okay. They typically have the general formula of CN H2N minus 2. So how do we synthesize an alkyne? Okay, the one logical reasoning would be, well, why don't we take a double bond and then convert it into a triple bond? And which again is, if a compound is an alkyne, it contains a triple bond, right? Very good. So how about we start with a compound that contains a double bond and then convert it to a triple bond? All right, and like I said, one of the easiest way to do it would start with something that already has a double bond. So for instance, I'm going to pick this compound right here. Okay, that's a compound that has a double bond. So here all the reactants that we're going to use, okay, this is everything. So that's typically the way when you learn an organic chemistry class or anything. This is an overall summary of all the reagents that are used in the reaction, okay? And the typical product you would end up with would be basically, if you add a double bond, if you add a bond, you got to get rid of hydrogens, right? If you remove bonds, then you add hydrogens, right? That's kind of what we've learned so far. So if I were to add a bond here, that means I must lose hydrogens on both the carbons that contains the double bond, right? And there we go. So how does this actually work? Which leads us to the mechanism. Okay, and I've said that just repeatedly. For most practical purposes, if you know the top reaction on what happens, then you most likely will be able to achieve the result that you're looking for, because most professional exams outside of a typical organic class, mechanism is not so much tested. It's actually the overall reaction that you would be looking for. So let's go ahead and write this up. Okay, so typically what's written on the top is what is first used. Typically what's written on the bottom is used consecutively. So which means the first part of the reaction is this alkene. If you're wondering what the name of it is, it's 4 carbons and it's 1, 2, 3, 4. So it's 1 butene, right? Just a refresher. I know it's been a couple of months since we have learned naming alkenes, so it's a good practice. So this now reacts with the Br2, and dichloromethane is actually a solvent, so it's not something that's actually involved in the reaction. It's just the reaction medium. So if you remember from what we learned for the previous material, whenever you have a double bond and you have diatomic halogen, then it tends to add to both the carbons containing the double bond, and typically it adds in a trans position. So that means I'm going to switch colors here and add the blue. Okay, let me switch back to blue. So the Br would add here and the Br would add here. Okay. Now at this point, I'd like to remind you of a couple of things that you may want to know. One of them is a nucleophile, something we will come back over and over and over again and discuss this concept. A nucleophile is something that's negatively charged, typically is negatively charged, okay, or electron rich, okay. Most people tend to think nucleophile has got something to do with nucleus. It's just the way they call it. Okay, typically a nucleophile is a substance that's rich in electrons or negatively charged. Let's get a different color for our electrophile. And an electrophile, I mean, you have to remember this, or you will remember it by practice, is typically electrophiles are positively charged and or electron deficient. Okay. Okay. This is very important that you remember this, simply because this is not a term or terms that we will just learn for this particular video, just this component of a video, and then just forget about it. This is something we will come back over and over and over again. So hydrogen is the most electrophilic substance, okay, because hydrogen exists as H+. Okay, this is an electrophile. Okay, so anything that has remotely a negative color, okay, negative shade to it, negative charge to it, would tend to be a nucleophile. And that's the idea that you need before we proceed to the second phase of this reaction, which is KOH, right? Now, KOH is a base, okay? Potassium hydroxide, it's what KOH stands for, is a base, and in liquid phase, it exists as K plus and OH minus, okay? Now, this is what we really are interested in, is the OH minus, which is the nucleophile. So when you have positive and negative going, that means the only likely reaction is the negative reacts with the positive, right? So where you cannot just remove hydrogens anywhere you like. You can only remove the hydrogens from the carbons containing the two BRs that we just added. So what happens here is I am going to actually rewrite this molecule in a certain way. Again, this is purely for the mechanism purpose, okay? So CH3, CH2, I'm going to write it this way. Instead of it, you know, sticking, instead of the hydrogen being placed right next to it, I'm going to write it this way, okay? Now let me go get a different color. Now what happens here is it's a two-step process, but it all works in the same, it all happens like it happens in one step. So what happens here is the OH minus comes, keep in mind this structure, the bottom structure is no different than the top one. It's just, it's a little bit more expanded than the top structure, okay? So the OH minus is a nucleophile and the hydrogen is an electrophile. So nucleophile prefers an electrophile because nucleophiles are negatively charged, electrophiles are positively charged. So it comes and grabs this hydrogen, and it's very important you pay attention to my arrows, the way I move them, okay? It only grabs the hydrogen. That means the bond here is going to actually, I'm going to write the BR here. Hang on a second. I'm going to write the BR here and the hydrogen here. Okay, so it's easier to see. So it really doesn't matter you write on the top or the bottom. So I'm going to write it this way. So the BR comes out. Okay. So what happens here is we have a sequence of bond moved and formed, right? So in the first step, okay, so we have made this. So CH3, CH2, CBr, right? Double bond CH, right? Bond CH, bond H. I'm going to leave this undisturbed. Now let's go get another color, perhaps maybe a blue or shades of blue. Okay. Keep in mind, as I've always said, just because one KOH is written doesn't mean there's only one KOH. Chemistry doesn't work that way. Okay. So there's another OH that comes, grabs this hydrogen, move this bond over here, and in the process, this has to come out. You may wonder, why does the Br has to come out? Well, if it doesn't, what happens? It takes us back to the first or second class where I said carbon cannot have more than 5 bonds, right? So you have, if you bring this here and you don't get rid of it, this carbon now has 5 bonds, okay? And that's not something you can have, right? And that's why, and Br is a better leaving group, so it's got to leave, so which leaves us with our ultimate product, which is CH3, CH2, C, triple bond, CH. There you have it. And this is the mechanism for how the reaction works. But the overall synopsis is that when you start a compound with a double bond and you treat it with a diatomic halogen and then a strong base such as KOH, then you end up with a triple bond over a double bond. All right. And this is the first of the ways we can synthesize a triple bond. All right. All right. Stay tuned for more videos.